This is the tutorial to first numerical. Tutorial to first numerical. Like something. In a radially inward flow turbine, the diameter of the runner at the inlet is 50 centimeters and the diameter at the outlet is 15 centimeters. The speed of the machine is 1500 rpm. The fluid and leaves the runner without flow component. The flow component of the fluid velocity remains constant in runner, the specific work and the degree of reaction. So this is what they're asking. There in the numerical we are supposed to solve for it. So before actually solving it, let us look at what is the data that is given. Okay, let's try to solve it. Solution. What is given in the problem statement? So they have given the outer diameter, which is 50 centimeters. I can write in terms of meters. I can write it as 0.5 meters. Centimeters. I can write it as 0.15 meters. And the speed with which the turbine is rotating is 1500 rpm. Okay. And the velocity with which the fluid enters, that is absolute velocity V1, is equal to 35 meters per second. And I do have alpha 1 actually. That is, it is making angle of 50 degrees. The fluid is entering at 20 degrees tangent to, so the alpha 1 is equal to 20. The whole component is 0. That's the meaning of it is my VW2 is equal to 0. And then they are telling the flow component in the fluid remains the same. The meaning of it is actually the flow component is VF1 and VF2 is equal to some value. That means they remain same. Okay. So here they are not given what is the mass flow rate. So let's assume the mass flow rate as 1 kg per second. Okay. What we are supposed to find? We are supposed to find. Let's try it one by one. The first thing is I need to find the blade angles at the inlet and outlet, that is beta 1 and beta 2. And the second one is the specific work, that is W by m dot. Okay. And the third is actually it is the degree of reaction R. So these three components we are supposed to find. First, so whenever we try to solve this problem, try to understand the sketch. That means the velocity triangle first, then we'll try to solve it actually. So let's try to put that actually. So if I try to put this, so this is my outer diameter. Okay, this is my inner diameter, and I do have a blade. So the blade is something like this. So this being a turbine, so this will be my leading edge. Okay, this will be my, okay, so this is the leading edge. I call it as 1, and the trailing edge I call it as 2. So that's where my fluid is entering. So let us try to draw a simple tangent over here. Okay, so let's try to draw a tangent. So let's try to draw a tangent here at this particular point. Okay. Fine. So same thing you try to do at point 2 also. What are these actually? Those are tangents. Why I am drawing this actually? Because your velocity triangle are running to that. You need not write every time. Now, this being a turbine actually. So this being a turbine, so what will happen? I do have a pressure side and do have a suction side. So the fluid will start rotating. That means your turbine will start rotating in this particular direction. So now, if you try to measure the blade angle, this is my beta 1 and this is my beta 2. if I try to measure the blade angle beta 1 and beta 2. Now, let us try to draw the velocity triangle. See, the fluid enters at some velocity v1. Okay, the fluid enters at some velocity v1. So that is around 35 meters per second. Okay. Now, there are two methods of solving this problem. Either I can go with a graphical method. So usually we try to do it in the steam turbine part. Actually, we take the graph sheet and do everything with respect to scale. Otherwise, we'll try to do a triangle, an approximate velocity triangle. Method, I will try to show you how to draw this approximate velocity triangle and use the trigonometric principles and try to solve it. Okay. Now, so V1. So V1 is the velocity with which the fluid enters. Let's say, try to draw it. So it is in this direction. So this is my V1. Okay, this is my V1. And then I have the your relative velocity. So relative velocity is always, it is always tangent to this particular thing. This is my VR1. Okay. Now, if I try to draw a line parallel to this particular tangent, okay, this particular to tangent, let me draw a line. Okay, this is how you have to. So if you try to measure that particular thing, this will be always your U1. Okay, that will be your U1 component. Now, I have, what will be this angle? This will be your beta 1. This will be your alpha 1. That will be your alpha 1. Now, what are the two components of velocity V1? So, I have one component of velocity, which is in the flow component. This will be exactly making an angle of perpendicular. That is, this will be my VF1. Okay. Then, I have one more component of velocity. That is VW1, which is in this direction. Okay. So these are the components. I have written all the component velocities here. Okay. All the components of velocity written here. Okay. All the components of velocity are written here. And this is my inlet velocity triangle. Now, see, it's easy to draw the exit velocity triangle. Why? They clearly told that my VW2 is equal to 0. That means I have only V2 component and VF2 component. That is, V2 is equal to VF2, whatever it may be. So if I try to draw the exit velocity triangle, it will be simply a straight line, like the right angle triangle. It will be, this is how it is. This is V2 is equal to VF2, because my VW2 is equal to 0. Then I do have my relative component. This will be in this direction. This is going out. Yeah, it will be in this direction. This is my VR2. Then I have the component of velocity, that is your U2. This is my U2. Okay. Now, if I try to, this is always perpendicular. Look, this is perpendicular, and this will be my alpha 2. This is my your what is called as your alpha 2, and this is beta 2. This is alpha 2, which is 90 degrees, and this is my beta 2. And this is my VR2, U2, and your V2 is equal to VF2, because my VW2 is equal to 0. So I am able to draw the velocity triangles based on what is given. Suppose if VW2 is not 0, then what would have been my triangle? My triangle would have been like this. So my triangle would have been, so suppose this would have been my VR2, this would have been my V2, and I would have got a U2 like this. So because my VW2 is equal to 0, what is happening? This is pulled to this way such that my tangential that is the world component of velocity, that is V2, this is VF2 actually. This would have been my VW2. Okay. Now this VW2 is equal to 0. So because of this particular thing, I am getting only the the triangle of this portion. That's it. I am getting a right angle triangle. So that this is my alpha 2. Now this becomes my alpha 2. This is my beta 2. This is how you are supposed to draw your velocity triangle. So once you are able to draw your velocity triangle, then I can easily draw the use the velocity, maybe your trigonometric principles, and try to solve the other components of velocity, whatever is missing. Now let us try to do one by one. Now, before we go ahead, what are the peripheral velocity, a blade velocity? Let's try to calculate one by one. See, the blade velocities are at inlet and outlet. So what is the formula? It is u1 is equal to pi into d1 into n by e. Okay, that is pi into 0.5 into 1500 divided by 60, getting around 39.27 meters per second. Okay. Now what is my U2? U2 is equal to pi d2 n divided by 60. So this is 5 into 0.15 into 1500 divided by 60. So U2 is equal to 11, getting 11.78 meters per second. You can verify this particular. I'm trying to put whatever values I'm getting from the triangle, my calculator. You can verify this. So once I got my U1 and U2, so this is as per see. I can redraw this all the triangles on a graphical sheet. I can do it. I can cross verify. Then I will get the exact size of the velocity triangle. And what I have drawn is an approximate one. Okay. Now, so what is my? Let's try to consider one by one. So consider the velocity triangle. Consider the velocity triangle at inlet, which is 1. Okay. Let us go back and see. This is the triangle, what I call it. So this is the inlet velocity triangle, and this is the outlet velocity triangle. Now, if I try to look into this particular inlet velocity triangle, what is cos alpha? Cos alpha is nothing but your adjacent side divided by your opposite. That is VW1 divided by V1. Okay. Then what is my sin alpha? Sin alpha would be VF1 divided by V1. So opposite side by your hypotenuse. So using your trigonometric principle, cos alpha 1 is equal to your adjacent, that is VW1 divided by V1, or VW1 is equal to V1 cos alpha 1. So V1 they are given as 35 into cos 20, alpha 1 is 20 degrees. If I try to calculate, my VW1 is 32.89 meters per second. So all are vectors. Now similarly, sin alpha 1. Sin alpha 1 is equal to your opposite divided by your opposite by your hypotenuse, that is, then Vf1 is equal to V1 sin alpha 1, that is 35 into sin 20. If I do that, so my Vf1 is equal to, okay, I try to calculate it, I am getting around 11.97 meters per second. I got my VW1, that is velocity whirl at inlet, and my flow velocity at inlet. See, there is a condition they given. What is it actually? The flow velocity remains constant throughout your turbo machine, okay, or the runner. So in that case, what I can do, Vf1 is also equal to Vf2. That means Vf1 and Vf2 both are 11.97 meters per second. Okay. Now let us try to find one by one. That is beta angles. Okay. That is, first one is blade angles. Blade angles beta 1 and beta 2. Okay. Now let us come back to the same velocity triangle. First inlet velocity triangle. So what is tan beta 1? Tan beta 1 is equal to Vf1. Okay. Tan beta 1 is Vf1 divided by u1 minus v2. So this distance, that if I call this distance as x, let me call that as x. What is x actually? X is equal to u1 minus vw1. Okay. So tan beta 1 is equal to Vf1 divided by x. Okay. Let me write that. So from the inlet velocity triangle, tan beta 1 is equal to Vf1 divided by x, which is equal to Vf1 divided by u1 minus vw1. So all the things I know actually. So this is actually 11.97 divided by u1, just now we calculated, which is 39.27. So vw1 is 32.89. You take tan inverse of it, I am getting my beta 1 is equal to 61.94 degrees. So I got my inlet blade angle. This is all from the inlet velocity triangles. Okay. Now, if I want to find beta 2, I should consider the outlet velocity triangle. Consider the outlet velocity triangle. Let us go to this actually. Now from the outlet velocity triangle, what is tan beta 2? So tan beta 2 is equal to, if I try to write it, tan beta 2 is equal to Vf2 divided by u2. So Vf2 divided by u2, opposite by your adjacent. So I can go and substitute this and try to calculate my beta 2 because Vf2 is equal to Vf1. So tan beta 2 is equal to Vf2 divided by u2, or I can write 11.97. So your u2 is 11.78. Okay. And one note is actually Vf2 is equal to Vf1. This is given in the numerical statement. Now if I take 11.97 divided by 11.78, tan inverse of it if I take, I am getting my beta 2 is equal to 45.45 degrees. So I got both my inlet as well as my exit velocity triangles. So once you got this blade angles, what is the second thing I am supposed to find? Specific work. Specific work. Okay. So what is the formula for the specific work? Actually, it is W by mass flow rate, and we have made an assumption that M is 1 kg, actually 1 kg per second. So what is the formula? W by M dot for a turbine, it is VW1 into U1 minus VW2 into U2. What is this actually? This is your Euler equation. And also in the numerical they have given that VW2, that is velocity of the whirl at the exit, is 0. So VW2 automatically becomes 0. So I am left with only VW1 into U1. So VW1 is how much? It is 32.87. And what is my U1? It is 39.27. Okay. What I'm going to get actually, I'm getting around 1.291 kilojoules per kg. So this is your specific work. That is W by M dot. Okay. Then what is the degree of reaction? The third one. We are supposed to calculate the the degree of reaction R. Degree of reaction R. So what is the formula? Degree of reaction, if you define it actually, it is nothing but your, what is it actually? Your static energy to your total energy. Okay. Static energy to your total energy or total head. This is the definition. See here, so directly I can use different formulas, or I can calculate it based on some kind of an whatever V is available. So whatever the fastest way I can do it. So here if you closely observe, if you go by formula, so this is the formula what we have defined actually. U is equal to your U1 square minus U2 square, okay, divided by 2 plus VR2 square minus VR1 square by 2 divided by your total work, that is your W. Okay, so W by M, whatever we have. So you can go by, so that particular thing, that is your W by M dot. So if you go by this particular formula, I have to calculate VR2 and VR1, which is not calculated. I can do that. You can do that and you can find it. Also, you can use another formula. What it is actually? R is equal to, see, you have your total work. What is your static actually? Your W, see, if you look into this particular formula, what is your W? W is equal to V1 square minus V2 square by 2 plus U1 square minus U2 square by 2 plus VR2 square minus VR1 square by 2. Fine. Now, this is your static, this is your dynamic quantity. So I can write W minus V1 square minus V2 square by 2 is equal to U1 square minus U2 square by 2 plus VR2 square minus VR1 square by 2. So what I can write? I can write it as W is equal to W minus V1 square minus V2 square by 2, okay, the whole thing divided by your W by dot M. This is W dot M. So in this case, if I see, I can use either this particular formula, what is there, the right hand side, this one, or I can simplify the same thing because I know this particular thing. I know this particular thing. So whatever the way, maybe in the how fast you people can do, it all depends on you. Now if I go use this particular formula, V1 I know, V2 I know, W I know. So only substitution. Otherwise, if you use the right hand side formula, I have to calculate VR2 and VR1, which may be another, it may take another 5 to 10 minutes. I will end up with the same number. So I'll use the first one. So what I will do actually, I'll use this particular thing. So R is equal to, okay, W by M is how much actually? If I can go with kilojoules, or I can directly write in terms of joules actually. This will be 1291 minus 35 square is my V1, so 35, so 11.97, because V2 is equal to VF2, okay, everything I am converting it to joules actually, divided by 1291, okay, R is equal to 0.58. So in the numerical statement, they have asked us to find the blade angles at inlet and exit. So this is the blade angle at the inlet blade angle, and this is the blade angle at the exit, that is beta 1 and beta 2. And the second quantity they asked us was, this is my specific work, and the third quantity they asked us was degree of reaction. All the components which they have asked in the numerical has been solved. This is how you are supposed to solve this numerical. The same methodology can be applied for even for a compressor or a pump. There, the only thing that's going to change is the way the velocity triangle is you are going to write. It may be from inlet to outlet or outlet to inlet. That's the only thing. So the methodology will be this one. Whether they will ask you to find degree of reaction, or they may ask you to find utilization factor, or they may ask you to find the blade angles, or they may ask you to find the work, or these are the things which you are supposed to find actually. Is that clear? So any doubts? So you can ask me. If there are no doubts, we'll move to the next problem. Okay. Let's move to the next problem. What is it actually? At a stage of an impulse turbine, the mean blade diameter is 0.75 meters. Its rotational speed being 3000 rpm, the absolute velocity of the fluid discharging from a nozzle inclined at 18 degrees to the plane of wheel is 275 meters per second. If the utilization factor is 0.9, the relative velocity at the rotor exit is 0.9 times that at the inlet. Okay, find the inlet and exit rotor angles. That is your beta 1 and beta 2. Also find the power output from the stage for a mass flow rate of 2 kg per second and the axial thrust on the shaft. So this is the problem statement. Okay. Now let us try to, so this is an axial flow machine. This is an axial flow machine. So what we'll try to do here, we'll try to use what is called as a combined velocity triangle. So instead of writing the velocity triangle separately, so we'll try to combine the because with a common base. I will show you how to do that actually. So now let us try to find a solution for it. Solution. Okay. So given, what is given actually? It is a common diameter, that is the mean diameter. Let me call it as a D is equal to 0.75 meter and the speed N is equal to 3000 rpm and alpha 1 is equal to 18 degrees. V1 is equal to 275 meters per second and your utilization factor, that is epsilon, is 0.9. The relative velocity at the exit is equal to 0.9 times the relative velocity at the inlet. That's the meaning of it. Okay. Then your mass flow rate is 2 kg per second. Yeah. What we are supposed to find? We are supposed to find the first one, the blade angles. Okay. The roll beta 1 and beta 2. Okay. That is, find the inlet and exit rotor angles. Rotor is nothing but your what we call it a hub or whatever it may be. So it's a blade angles only. The second one. So it is the power produced or whatever it may be. It is power or W by m dot whatever power. Then the third one, you need to find the axial thrust. These are the three quantities which we are supposed to find. See here, I do have a common velocity, that is your u. So let's find that. So your common blade velocity, the blade velocity, which is u is equal to pi d n by 60, okay, which is pi into 0.75 into 3000 divided by 60 is equal to, I am getting around 117.81 meters per second. Now, so this is the blade velocity. If I try to have a combined velocity triangle, look at this. I am going to use what is called as a combined velocity triangle. What it is actually? It is a unified velocity triangle with a common base. See here, my u is same. My u is same. What I am going to do actually? I will have a common u, which is like this. Okay, and for this I do have a V1, something like this. This is my V1, and then I have my VR1. Then I have a V2, then I have my VR2 like this. So this is called as a combined velocity triangle. And if I try to write the corresponding blade angles and all for this, so let me complete the triangle. Let me complete the triangle. Okay. So this is my triangle, and if I try to, this is my alpha 2, alpha 1, this is my beta 2, this is my beta 1. Okay, so this will be VF2, this will be my BW2. Okay, then this will be my BW1, and then this will be U actually. This will be my U, which is common. This will be VF1. So whatever, if I try to name it actually, if I call this as A, B, C, D, E, F. So A, B, C is the inlet velocity. A, B, C, D is the inlet velocity triangle. Okay, and your E, B, say B, E, A, or B, E, F, A. So the whatever is there to the left hand side is my outlet velocity triangle. So I do have outlet velocity. This is my outlet velocity triangle, and this will be my inlet velocity triangle. See, I can easily draw this kind of a triangle to solve a problem. This may be bit, see, this is how you are supposed to solve it actually. But I will show you how I got this triangle. I will show you how I got this triangle. Now, as I told that, in case of an axial flow machine, what we try to do actually, suppose if I have a, this is my blade profile, what I am going to have, and this is my blade actually. This is the blade, what I'll be having. Okay. This is the blade. It's an axial flow machine, and it is rotating in this direction. This being a turbine. Okay, because this is my pressure side, and this is my your suction side. Now I'm trying to draw this particular triangle. See, I was supposed to draw this kind of a triangle there. So what it is actually, I'm going to draw the triangle. So same triangle what I showed here. No, this triangle I'm going to draw it here. So I have the inlet, that is your V1 will be in this direction. So this will be my V1. Okay. Then I have your relative velocity. Okay. The relative velocity will be somewhere like this. The relative velocity I can, this is how it is actually. This is my relative velocity, and I'll be having the a U like this. This is my velocity triangle, whatever I have. Then what will happen at the exit? So exit, it will be something like this. So this is my velocity, that is V2, and I have the blade velocity, which is all your relative velocity will be in this direction, because this is always the VR2, this should be always tangent to the blade, tangent to this particular blade, right? I have my U, which will be like this. Either I can draw this kind of triangles for an axial flow machine. Look at this. Why it is actually? This is an axial flow impulse machine actually. Either I can draw in a combined velocity triangle like this, or I can draw a velocity triangle like this. So both will give the same result. So I can have, this will be my VF1, okay, this will be my VW1, okay, then this will be my VF2, and this will be my VW2. If I try to draw it, this will be alpha 2, beta 2, this will be beta 2, alpha 2. Okay, why this particular, if I try to measure it, this will be my beta 1, and if I try to measure somewhere here, this will be my beta 2. So this is how your velocity triangle, if I write it separately, an axial flow machine looks, or if I try to combine and draw a combined velocity triangle, this is how it should be written. So both are correct. Either you can go with this way, I can draw a separate velocity triangle for an axial flow machine like this, fine, or I can have a combined velocity triangle. So this is for the axial flow machines. Now to solve it actually, I am going to use the trigonometric principles. Okay. Now let us consider the inlet velocity triangle. So it's very similar to your previous problem. We are supposed to find beta 1, beta 2, your power, and the extra thing what we have is axial thrust. Okay. Now if you here, I know, see, I know the value of alpha, which is 18 degrees. I know the value of V1. I'll go with the same thing. So what is it actually? This is my alpha 1 and beta 1. So what is my sine alpha 1? It's once again your Vf1 divided by V1. And what is my cos alpha 1? It is Vw1 divided by V1. So I can find my flow velocity and world velocities at inlet. Similarly, what we found in the previous problem, very similar to that. Then I can find, see, if I call this as x. This is x here, and this is your x here. If you want, you can cross check. After I solve the problem, you can cross check using both whether I'm going to get the same thing, because I'm using trigonometric principles. I am not using anything else. We'll end up with the same solutions. Okay. Now let us consider the inlet velocity triangle. That is that it is 1. Okay. So what is sine alpha 1? Sine alpha 1 is equal to Vf1 divided by your V1, or Vf1 is equal to V1 sine alpha 1. What is my V1? It is 275. They are given 275 into sine 18. If I try to put into my calculator, I am getting 84.98 meters per second. This is my flow velocity at the inlet. So similarly, what is my cos alpha 1? It is Vw1 divided by V1, or Vw1 is equal to V1 cos alpha 1. If I substitute, it is 275 into cos 18. I am getting my Vw1 as 261.54 meters per second. Okay. Now what is this x actually? X is Vw1 minus u. Okay. I can find that. So x is equal to Vw1 minus u actually. So this is 261.54 minus What is your U actually? It is 117.81. Yeah, 117.81. 117.81. I am getting 143.7 meters per second. Okay. Now, how to find the blade angle? What is tan beta 1? So, if I use this particular triangle, I am trying to use this particular triangle. If I use this triangle, what is tan beta 1? Vf1 divided by x. If I use this particular triangle, what is my tan beta 1? Once again, it is tan beta 1 is equal to Vf1 divided by x. So both are same. So if I go and substitute this, so tan beta 1, that is blade angle at inlet. So to find the blade angle, tan beta 1 is equal to Vf1 divided by x. Or what is my Vf1? It is 84.98 divided by 143.7. Take tan inverse of it. I am getting around 30.59 degrees. I got my inlet blade angle. Okay. So I need to find the, see here, from the, I need to find VW1 or VW2. Some of the things I need to find. So to do that, what I'm going to here, I don't know the value of relative velocity. I can find relative velocity in two ways. Okay, sine beta 1, see, if I try to go and look into this particular velocity triangle, what is sine beta 1? Sine beta 1 is equal to Vf1 divided by Vr1. What is cos beta 1? It is x divided by Vr1. So if I want to find Vr1, either I can use either cos beta 1 or I can use sine beta 1. So either of the trigonometric formulas I can use it. So to find Vr1, okay, I can use sine beta 1 is equal to Vf1 divided by Vr1 or cos beta 1 is equal to your x. What is x actually? X is equal to Vw1 minus u divided by Vr1. So both the way I can find it. So if I try to use the first one, Vr1 is equal to Vf1 divided by sine beta 1. That is Vf1 is 84.98 divided by sine 30.59. I am going to get Vr1 is equal to 167, roughly 167 meters per second. Now look at this. In the numerical, what I have given? Vr2 is equal to 0.9 times your Vr1. So in that case, it is 0.9 into 167. So your Vr2 is equal to 150.27 meters per second. Okay. Now what is your utilization factor? So utilization factor is nothing but it's the utilization of your energy to energy that is maximum. Energy utilized to energy that is maximum. So I can find like this. So utilization factor is equal to, it is the energy utilized divided by your energy plus your V2 square by 2. Already you have this particular formula. What is this W? This W is nothing but your VW1, okay, minus VW2 into U. Why it is only U? Because it's an axial flow machine, divided by VW1 minus VW2 into U plus V2 square by 2. Okay. So this is a formula what we have actually. So VW1 I know. I don't know the value of VW2. I can find VW2. I can find VW2 based on the value of 0.9. What based on my epsilon? I need to find that. Now let us look at this VW2. Where is my VW2? Whether it is positive or negative, this is the formula. Now what I'm going to do actually, I'll try to put this in this particular formula, the value of my VW2. Okay, so I'm trying to utilize 90% of it. Okay, so VW1 is, just now we calculated, is 261.54, 261.54 minus VW2 into U is 117.81 divided by, okay, 261.54 minus VW2 into 117.81 into 117.81 plus, what is your V2? See, what is your V2? I don't know the value of V2. How to find the V2 actually? See, V2, I need to find it from your exit velocity triangle. So from your exit velocity triangle, I need to find V2. So V2 can be found in different ways. So how to find that V2? I need to find this V2, then substitute over here. So V2 is equal to your V2 square plus your VW2 square. So using your trigonometric principles, I can find that. If I know my VF, if I know my VW2, I can find that. I can find the corresponding other things also. Or go back and look into this. So if you go back and see here, I don't know the value of I don't know the value of V2. Or you have another formula where there is a relationship between your degree of reaction and your absolute velocities, being an impulse machine. So for an impulse machine, I'll give you that particular formula, you can use that. So for an impulse machine, see, or any general machine, you have this formula. Epsilon is equal to V1 square minus V2 square divided by V1 square minus R into V2 square. So this is a very general formula to find relationship between, this is the formula, we are not deriving it actually. So this is the relationship between your epsilon and V1 and V2. This is the formula. And your R. So this is the formula. Now, in this particular case, R is 0. So what will happen to your epsilon? For R is equal to 0. For R is equal to 0, your epsilon will be V1 square minus V2 square by V1 square. So I can easily find, V2, that is 0.9 is equal to, what is my V1? It is 275. Okay. So V1 is equal to 275. It's clearly given in the formula, that is 275 square minus V2 square divided by 275 square. I will end up with V2, which is square root of it. I'll end up with V2 is equal to 86.96 meters per second. I can use this formula and find your V2. Once I find this V2, okay, once I find this V2, I'll go to this exit velocity triangle. So in the exit velocity triangle, if I consider V2, VW2 and VF2, if I consider that as a right angle triangle, I can clearly tell V2 square is equal to VW2 square plus VF2 square. So I know the value of V2, I know the value of VW just now, so I know the value of your VW, I can find the VF2. I can find the VF2. So once I find the V2, so I can by VF2, I can find the exit blade angle. Easily I can find it. So that's what I'm going to do. So from the exit velocity triangle, from the exit velocity triangle, V2 square is equal to VF2 square plus VW2 square. So this is 86.96 square is equal to your VF2 is what I'm going to find plus your VW2 is 27.3. So which I'm supposed to find. Yeah. So here, yeah, from this I need to find VW2. So because once I find this, which is 86.96 96 square by 2. So from this, if I substitute 86.96 from V2, I need to find V2 here. If I substitute and find it, I am getting my VW2 as 26.3 with a minus sign. 27.3 with a minus sign. So what is the meaning of it actually? The VW2 is in opposite direction. That means, see, if VW2 is in this direction, this is my VW1, this is the direction of your VW2, that is the meaning of it. That means what it is actually, this velocity triangle, this, whatever I have drawn here, no, this particular velocity triangle, it is, I need to change it. So I need to draw the triangle in such a way that this goes to other side of it. That means my velocity triangle should be something like this. Okay, this is my VR2 and my V2 should be going in this direction and this will be my U2. So what I have written in the combined velocity triangle, this is what I am going to get. At the end, you will be able to get the exact velocity triangle based on the values. So this is my final velocity triangle. See, what I have written initially, maybe it's an approximate. So once you are able to get the values of it, then I'll be able to get the velocity triangle, final velocity triangles. So which will be very similar to your combined velocity triangle. So now, once you find this VW2, substitute over here. So what is it actually? It is minus 27.3. It is square. If I do that, I'll end up with VF2. If I take square root of it, all those things, which is 82.54 meters per second. So once I'm able to find this, I'll be able to find the blade angle, which is tan beta 2 is equal to VF2 divided by VW2 plus U, and if I take the tan inverse of it, all those things, tan inverse of your VF2, which is 82.54 divided by VW2 is 27.3, which is a minus plus 117.81. So I'll end up with somewhere around 28 degrees or something. 28 degrees is what I'm trying to get it. So we'll stop here actually because already it's time, and we'll try to continue